So another couple of sensors that we're going to look at are the ones that are used on stations 5 and 6 to sense the level of the pellets. The station 5 sensor is a digital sensor. It's a linear incremental encoder, and as the plunger moves down to hit the surface of the pellets, the sensor measures how far it moves by counting these little increments on the shaft of the sensor. With station 6, the sensor is an analog potentiometer, just a linear potentiometer with the slider that slides from a minimum voltage to a maximum. And so the voltage level coming out is a measure of the pellet level. So this is a close-up of the digital sensor showing with it in its retracted position and then extended down to the pellets. The digital sensor is a magnetic linear incremental encoder, which means the incremental means that it uses these little markers, and in this case it uses magnetic markers and a pickup head to count the markers as they go by. So the rod, as it moves back and forth, the pickup is picking up these magnetic pulses. Now these pulses are going to be fed into a counter, a PLC counter module, and the counter has to be able to know not only how far the rod is moved, but also the direction of movement. So the technique is used in all kinds of encoders, which is called quadrature encoding, where there are two pickups, two magnetic sensors. One of them is 90 degrees out of phase from the other. So what happens when direction changes, the phase relationship between A and B change, and that's what allows the counter to know whether the direction is changed and whether to count up or count down. So that's the basic idea. Same principle as you would have on a rotary encoder on a electric motor. It's the same exact principle with the two encoder channels. So the output stage looks like this. It's the encoder output uses open collector transistors, and these are just Zener diodes to protect the transistor from excessive voltage, but they don't really affect the function. So because they're open collector, when you hook them up to the high-speed counter input, an open collector can only short to ground or open circuit, so the counter input needs a logic high and a logic low, and so these pull-up resistors are used so that when the transistor is off, the output or the input of the encoder is pulled up to 24 volts, and then when the transistor turns on, it pulls it down to 0. So that gives a nice sharp square wave going from 24 to 0 as the pulses come out of this encoder. So this is the actual electrical diagram from the HAS200 schematics. So you can see the encoder here, the two outputs, the channel A and B outputs, and these are the two pull-up resistors. Those are IEC symbols for resistors. They don't use the zigzag symbol, they use this little rectangular symbol. On station 6, the analog sensor is, as I mentioned, a linear potentiometer. So here it is retracted and the plunger extended. So inside this is just a potentiometer, and as the rod moves up and down, it moves this slider up and down the resistive element. These are the two symbols for potentiometer, the ANSI symbol, American, and the European symbol, IEC. So on the HAS200, the system was made in Spain, so they use all the European symbols. So there's a cable that connects the output of the linear pot to the analog module. So to connect to the analog module, the potentiometer is attached to two voltages. Now the only voltage that's available on the HAS200 is the 24 volt supply. The problem is if you were to connect the pot to 24 volts, the range of the analog input module is only 0 to 10 volts. So 0 to 24 is too much. So the solution they used for this system is to just put a resistor in series with the pot to drop 14 of the 24 volts across the resistor, and so the pot has 10 volts across it. It's actually not the best solution because it depends, the accuracy of this 10 volts depends on too many factors. It depends on the actual voltage coming from the supply and the tolerance of the resistor and the tolerance of the pot. A better solution would be to use a Zener diode as a reference, but we can talk about that in class. Here's the diagram from the Station 6 electrical diagrams. And so this is the linear potentiometer. This is the pin with the arrow on it is the slider. And so you can see one end of the potentiometer is connected to 0 volts. The other end has the resistor to drop the 14 volts from 24 down to 10 volts, and then the potentiometer has 10 volts across it. So as the piston moves up and down, that slider moves up and down with it, and you get a voltage varying from 0 up to 10 volts, which is a measure of the height of pellets. So that's the overview of the sensors. You're going to be working with most of these sensors in the lab, and so I will see you in the lab.